Probability now rests on three axioms: non-negativity, normalization, and additivity. Those axioms work on any sample space, but how you actually pin down a probability law depends on how big that sample space is. In this video, we sort probabilistic models into three families. First, finite sample spaces, then countably infinite ones, and finally, uncountably infinite sample spaces, where, as we will see, weighting individual outcomes breaks down and we measure probability by integration instead. Start with the simplest family, a finite sample space. When omega has finitely many outcomes, a probability law is completely determined by the probabilities of those individual outcomes. The probability of an event A is just the sum of the probabilities of the outcomes it contains. There is one especially clean case, the equally likely model. For equally likely outcomes, each of the n outcomes carries probability 1 over n, and the probability of an event A is just the size of A divided by the size of omega. Take a fair die, 6 faces, each with probability 1/6. To find the probability of an event, we count. The event roll of prime is the faces 2, 3, and 5, 3 favorable outcomes out of 6, so its probability is 3 over 6, 1/2. Favorable over total, exactly the counting model from Chapter 2, now named. One warning. Equal likelihood is a modeling assumption, not a law of nature. A loaded die, a biased coin, the sum of 2 dice, none of these have equally likely outcomes. Assuming they do is a common misconception called the outcome approach. Use the equally likely model only when a genuine symmetry of the experiment earns it. Now, let the sample space be infinite, but countably so. A set is countable when its elements can be lined up in a sequence S1, S2, S3, and on. Formally, it has the same cardinality as some subset of the natural numbers. Even though there are infinitely many outcomes, we can still specify the law one outcome at a time by assigning each a weight, as long as those weights sum to 1. The classic example: toss a fair coin repeatedly until the first heads and record how many tosses it took. The sample space is the positive integers 1, 2, 3, and so on, a countably infinite set. The probability that the first heads lands on toss k is 2 to the minus k, a half, a quarter, an eighth, a 16th, each bar half the height of the one before. Add up that whole infinite sequence of weights and it comes to exactly 1, just as the axioms demand. The masses fill the bar. And we can ask real questions. What is the probability that the number of tosses is even? Add the even indexed weights, 1/4 plus 1/16 plus 1/64, and on a geometric series that sums to 1/3, an infinite computation made finite by the structure of the model. The third family is the strange one, an uncountably infinite sample space. Take the unit interval, every real number between 0 and 1. There are so many outcomes here that most subsets cannot be written as a finite or even countable list, so the trick of summing individual outcome probabilities simply fails. In fact, on a continuum, almost every single point carries probability 0. There are far too many of them for each to hold positive mass. A mixed law can place a lump on a few isolated points, but a purely continuous law spreads its mass out, leaving every single point with none. So we specify the law a different way. For the uniform law on this interval, the probability of landing between A and B is just its length, B minus A. A general continuous law replaces length with the area under a density, an integral, and length is simply the flat density case. From there, the third axiom extends this to any countable union of disjoint intervals by adding their probabilities. Here is the idea in action, the wheel of serendipity. Spin a pointer on a circle. The outcome is the angle where it stops, uniform on 0 to 2 pi, an uncountable sample space. The probability of landing in any arc is the length of that arc divided by 2 pi. Land in the first quadrant an arc of length pi over 2, that is 1/4. Probability has become geometry, an arc over the whole circumference. So the family of a model is set by the size of its sample space. Finite and countable models weight individual outcomes, while uncountable models assign probability by integration, by length in the uniform case. That closes the core of Chapter 3. 2 topics remain: the continuity of probability, and the measure theory that puts all of this on a rigorous footing.